Welcome back. Now we will analyze what operating region in traction force and vehicle speed an electric powertrain has, and compare it with the vehicle requirements we have used in earlier analysis to determine how well it meets them. Then the operating region will be compared with that of the combustion engine powertrain to see both similarities and differences. When analyzing the combustion engine powertrain, we use the engine's operating region in torque and shaft speed, and the transmission model to determine the operating range of a combustion engine powertrain. Now we will do the same for an electric powertrain. Then we start from the operating region of an electric machine in torque and shaft speed to determine the operating region for the whole powertrain. To do the analysis, we need to know the transmission parameters. For this analysis, we assume a powertrain with a single gear transmission. The gear ratio is 2.5, the final gear ratio is 2.7, and the wheel radius 0.3 meters. This results in a total transmission ratio of 22.5 1 per meter. This is similar to the transmission ratio of the second gear in a combustion engine powertrain. Here we see the operating region and the efficiency of an electric drive system with a permanent magnet machine. The operating region and the efficiency include the effect of both the electric machine and its power electronic inverter. This electric drive can produce 320 Nm of torque in both directions. The maximum power in motor operation is 118 kW and it is at 3,500 RPM. In an ideal electric machine, the maximum power would be possible to maintain also at higher speeds. However, for this machine, the maximum power is reduced when the speed increases above 3,500 RPM. The maximum speed of this machine is 12,500 RPM, which is about twice as high as for the gasoline engine. The minimum speed is not zero, but minus 12,500 RPM, since the electric drive system is capable of running also in reverse direction. It has exactly the same performance and limits in reverse and forward direction. Negative speeds have not been included in the diagram, as we will focus on analyzing only forward driving. The fact that the electric machine can run equally well in both directions means that an electric powertrain does not need a reverse gear. Since the transmission has only one single gear, each point in the operating region of the electric machine corresponds to only one operating point in the four-speed diagram. The translation is done using the transmission model and the total transmission ratio. This can be done point by point. Then we can plot the total operating range, which looks exactly as the electric machine's operating range. Notice that with just one gear, this electric machine provides a powertrain operating region which allows speeds from standstill up to more than 200 km per hour. Now we will use this powertrain operating region to see how the performance of this electric powertrain meets the requirements of a vehicle. We have assumed the same small vehicle as when analyzing the combustion powertrain in order to compare the results. Notice that an electric powertrain often is heavier than a combustion engine powertrain due to the battery weight. We have not included that difference in this comparison. This is the required operating point for driving at top speed on a flat road, and we can see it's just about met by the powertrain. These are the requirements for driving on 10% and 20% uphill gradients, and they are easily met. Accelerating 4 meters per second square at low speed and 50 km per hour set these operating points, and we can see that the powertrain can provide roughly 1.5 times the required force, so accelerating at low speed will be no problem for this powertrain. The acceleration requirements at 100 and 150 km per hour, 2.5 and 1 meter per second square respectively, are on the limit of the powertrain's operating region, so they can be met but not exceeded. It seems that the low-speed requirements are easier to meet than the high-speed requirements for this powertrain. To see why that is, we plot the curve along which the traction power is equal to the peak power of this powertrain, 118 kilowatt. With this curve as a reference, we can see that the electric machine is not capable of keeping the power constant as the speed increases. The peak power is only possible to produce close to 60 km per hour. When the speed increases above 60, the maximum power of the powertrain drops, and at high speeds it's only 85 kilowatt, which is only 72% of the peak power. This is a reason why this electric powertrain easily meets the low-speed requirements, while the high-speed requirements require it to use its full capacity. An electric machine can make the shaft torque negative, and when doing so, it is converting mechanical power into electric power and can charge the battery with it. Since the electric powertrain has this ability, we can also compare how well it meets the requirements for regenerative braking, which we presented in an earlier lecture. We can see that the regeneration requirements are well inside the operating region of the electric powertrain and can be exceeded by roughly a factor of 4. A fully electric powertrain like this is able to regenerate at high negative forces, simply because the capacity to do so comes for free when we require such high positive force. In some hybrid powertrains, the requirements for positive force from the electric machine will often be much lower, and then the requirements for high negative force may drive up the cost of the powertrain. So requirements for regenerative braking are usually more interesting when sizing mild hybrid powertrains, while they in most cases have little influence on the sizing of a fully electric powertrain. Now we will compare the operating region of this 180 kilowatt electric powertrain with the operating region of the 5-speed 100 kilowatt combustion engine powertrain. The gray area is the operating region of the combustion engine powertrain. We can see that at most speeds it has lower maximum force than the electric powertrain, which is partly because of a lower peak power of the engine, but also due to the limited number of gears, making it impossible to use the full engine power at all speeds. At high speed, the combustion engine powertrain can produce higher force than this electric powertrain, since the electric machine then only supplies 85 kilowatt. We can also see that the electric powertrain has the advantage of regenerative braking. Another difference, which is not reflected in the diagram, is that the electric powertrain has a much quicker response when the driver presses the accelerator pedal. This is because an electric machine can increase its torque in just a few tenths of milliseconds, while a combustion engine often requires several hundred milliseconds up to about 1 second to build up full torque. Additionally, this electric powertrain never needs to change gear, so it would provide a much quicker acceleration response in many cases. Despite these advantages, we see that the electric powertrain struggles with the high-speed acceleration requirements. If the high-speed performance can be increased, it would be possible to reduce the size of the electric machines, since it has no problem of meeting the low-speed requirements. A solution to that can be to add one more gear. If we add a second gear with a total transmission ratio of 12 1 per meter, we get this additional red operating range to select from. Notice that the second gear reduced the force at low speed a lot, while it only increased the force a little at higher speeds. The second gear also increases the theoretical top speed of the powertrain, but since the vehicle could reach 200 km per hour already on the first gear, this has no value for this vehicle. Still, what looks like small improvements in force between 100 and 200 km per hour still are in the order of a 20% increase in force. So it can either provide that much more performance or allow the electric machine to be made that much smaller. The reason why an additional gear could increase the force is that the electric machine could not keep the peak power as the speed increased. For an electric machine which can keep the power constant at high speeds, an additional gear will not increase the force. There may however be other reasons to use 2 or more gears. A second gear may be needed if it's difficult to simultaneously meet the low-speed force requirement and be able to reach the top speed with the same gear ratio. A third reason for more gears may be to increase the efficiency of the electric machine, even if additional force is not needed. Adding gears of course increase the response time of the electric powertrain in some situations. To summarize the properties of electric powertrains and compare them with combustion engine powertrains. An electric powertrain needs no clutch and has a simpler gearbox, as it is often only 1 or 2 gears. It produces constant force in low speeds, and at higher speeds the maximum force vary in a smooth way. However, at high speed the traction power is often reduced. It can regenerate power during braking and has a quicker acceleration response than a combustion engine powertrains. A drawback is also that battery electric powertrains are more heavy than a combustion engine powertrain due to battery weight, and that increases the force requirements on the powertrain. Now you have learned that you can use the same method to analyze the operating region of an electric powertrain as a combustion engine powertrain. The different operating region of the electric machine, however, lead to the electric powertrain having a different operating region than a combustion engine. Now do the exercises to practice how to analyze electric powertrains.